חלקי כאילו כזה. כזאת רמה. בהחלט יכולה. שמתי את זה על השולחן.
Yeah, but the test is work with the recording, not already. So I'm trying to test it.
Before I start the lecture, we need to discuss again the exam. And I will explain why. So, it turns out that the 4th of February is in some ways the worst possible choice because that's the time I will be on the plane. So I cannot be in any way responsive to questions if they arise. Now, there is also, from a formal point of view of the regulations of the university, was a problem because something happened which I guess shouldn't have happened, but the point is that there were two different dates that appeared on the Shnaton, right? At some stage it was the 4th, and then at some stage quite early it was changed to the 1st. So it's not even clear to us from the formal point of view what the regulations tell us, and we can try to check. I want to just bring up another possibility that we thought of, but this will require agreement of everyone, and this is to do it on Friday. So 1st of February is Thursday, 4th is Sunday. As I mentioned, 4th I cannot be present in any way. So this is also a possibility to do it on the 2nd, on the Friday.
It's not the same problem that we have with the 1st, that there's not enough time to study.
Well, it gives you one more day.
Well, it's recently for logical, I have another test on Friday.
I see. Okay, so I think this is ruled out.
And what about this is what we tried to do, and we didn't finish to collect all the signatures, to do it on the week of the 4th? Someday on this week.
I think this might be better, if you can agree on it, of course.
We are 2 people away from this.
Okay, so continue to work on it. I think from my point of view, I'm not sure, 5th might be also difficult just because I'm just arriving, but I will try to do my best. As I mentioned, 4th is, from the point of view of my availability, is the worst possible. Okay? So I'm open to, I mean, if we need to do it on the 4th, we'll do it, but then there's this limitation. So if you manage to agree on a later date on that week, I think that's better. Okay. We continue to discuss correlations. So I'd like to remind you, up to the last lecture, the end of the last lecture, we discussed independent neurons and how noise affects Fisher information, discriminability, estimation. And we started to discuss last time what happens if the noise in the different neurons is correlated. And what I did in the end of the lecture, it was just through some examples to show you that it's not a trivial question. I gave you an example, one example where we had identical neurons and then having correlated noise was bad. If the noise is identical in all the neurons, we don't gain anything from having more and more neurons. And so if they're uncorrelated, that's good. When we add more neurons, we can kind of average over the noise and get a better estimation. And then I gave you another example where the responses of the neurons were different. And then actually, if the neurons are fully correlated, that's good because we can eliminate the noise. We can just take the difference between the activity of two neurons, get something informative about the signal, and eliminate the noise. So what we want to do now is discuss this in more thoroughly. Thanks for asking. Okay, thank you. In general, as you see, I often forget to ask, so it's good that you raise this, and please try to do it. Okay, so okay, so I want to discuss a certain model, which will be more general than the examples, the very simplified examples that I discussed so far, and analyze it. So we imagine that we have a neural population.
What is the name of the model?
I don't give it a name. It's a model. It's a model. We have a neural population, and the responses are defined as follows. The mean of the responses which I will denote by R. So I'm not going to, for simplicity, I'm not going to think about the responses as discrete, as integer, a number of spikes. It's some continuous variable R. And this will be some function of the stimulus. And then on top of that, there will be some noise. So even if for a given stimulus the responses are stochastic, and the noise in them is correlated. So the correlations, which I will define clearly in a moment, will be pairwise correlations in the noise, and will be characterized by a matrix Cij, and I'll tell you in a moment how that defines the response of the neurons. Okay. So the most simple model that we can write that has these characteristics is to assume that the noise is Gaussian, and that's what I'll do. So therefore, P of R given theta is going to be written as a multi-dimensional Gaussian, and you went through the math of multi-dimensional Gaussians with Neta recently. So I will write it as some normalization factor times the exponent of minus half r. Let me see, I want to write it. Okay, I will write it with a sum over I and j Ri minus Fi of theta a matrix Cij minus 1 R j minus Fj of theta. Yes, Cij. So, okay, this is the ith jth element of the inverse of the matrix C. This is important to note that if the way I wrote it, it wasn't clear if this was Cij 1 over Cij. No, what I mean is the inverse of the matrix C, element ij. And so this is a general multidimensional Gaussian distribution, right? And as you know, with what characteristics? The mean of this distribution is indeed Fi for each element, and the covariance matrix of the responses is the matrix C. Now, what does that mean? It means that I'm assuming that the covariance of the noise is completely independent of the stimulus, because I did not tell you that Cij is a function of theta. Cij is just fixed. So this is our model. So one way to think about it is that the response of the neuron is this thing plus some noise. The noise has zero mean, and it's additive, and it has a certain covariance matrix in all the neurons. So these are our assumptions. Okay?
Why does the noise have zero?
Because by definition, if I say that the noise is Ri minus Fi, Ri is Fi plus noise, then the noise is Ri minus Fi, and then this is just that quantity has zero mean. The R has a mean Fi, Ri minus Fi has zero mean. The mean of, is that okay? The mean of R is F, the mean of R minus F, which I call the noise, has its mean is zero. Okay, and
So we assume the covariance matrix, the noise is independent, so
well, so the noise is no longer independent in the different neurons because it has a certain covariance matrix, right? But what we do assume is that the structure of the noise is independent of the stimulus, because Cij is independent of theta. And what we want to understand now is what the interplay between these functions and Cij on the ability to do what. So what we will discuss is discriminability. So imagine that there are some two values of theta, theta 1 and theta 2, and we want to discriminate between them based on observations of the responses. Since we only deal with two values of theta, then we also care only about these functions, the value of these functions for these particular values of theta. So let's just give that a name. Fi of theta 1, by definition, I will call Fi minus, and Fi of theta 2, I will call Fi plus. Okay? And what I'm going to discuss throughout our discussion on correlations is not a general discriminator, but a very specific form of a discriminator, which is a linear discriminator. So a general linear discriminator will be based on some linear combinations of the responses. W sum Wi, F Ri, where I goes from 1 to n. Let's say that we have n neurons. Okay. And so the structure of this discriminator, the architecture is that it's summing up the responses linearly and then thresholding. I'm not writing explicitly the threshold. We'll need to decide about the threshold, and we'll do that in a moment. All right. So given that that is the structure of the discriminator, what is the best, and suppose that I even tell you what are the WIs, what is the best strategy to discriminate between theta 1 and theta 2? Maximum likelihood. So we need to calculate the likelihood. So if I will give this a name, this quantity, I will give it a name. Let's call that LW of R. So I'm writing the W to remind myself that the WIs are some parameters. But with a given choice, if I tell you what is LW of R, you need to ask yourself whether it's more likely to get this value of L for theta 2 or for theta 1. So let's ask ourselves, how does P of L given theta 1 or P of L given theta 2 look like? How is that distributed? So given that the stimulus is theta 1, what is the likelihood to probability to get different values of L? How is that distributed? So it's a normal distributed variable. So this is a very key feature of normal multidimensional normal distributions, that any linear combinations of their elements is also a Gaussian distribution. So if it's a scalar, if we take just one, as here, we take some linear combination and generate from it a scalar, this will be normal distributed. If I take several variables like this, which we're not going to do now, but if I take several variables like this, they will be together a multidimensional Gaussian variable. Okay, so we know that this is a normal distribution. So if I plot it, this will be L. Sorry, this will be L. This might be P of L given theta 1. And this might be P of L given theta 2. It looks something like this. And assuming that the stimuli, let's assume that the two stimuli appear with equal probabilities, then it's clear that given the choice of W, so the choice of W will affect both the mean of these two distributions and their width. But for a given choice of W, it's clear that the best discriminator would be to threshold at this point, right? If P of L given theta 2 is more likely for a given observation of L, if this is more likely than this, I would, so if L is beyond this point, I will choose theta 2. If L is below this point, I will choose theta 1. Now, so what do we need to do? In order to understand what is the likelihood of making an error, we need to calculate the area. So, for example, imagine that theta is theta 1. I will choose theta 1 as long as I'm below this point. So the probability of making an error will be this area. And I need to calculate it. In order to calculate it, I need to know what is the mean of this distribution, what is the mean of this distribution, and what is the width. Can you say, okay, so what is the mean of this distribution? Let's call it mu1. What does that mean? What is mu1?
The weighted sum of the averages of the units.
This is L. We need the mean of this thing given that theta is theta 1. So what is that? Some W. Yeah, we need to take the means of Ri given F1, which is Fi minus. So this is sum of Ri, Wi, Fi minus. And likewise, mu2 is sum over I, Wi, Fi plus. We also need the standard deviation. Is there anything that you can tell me immediately about sigma 1 and sigma 2? Yeah, they will be the same. Why will they be the same? Because these two distributions have different means, but once I subtract the mean, everything that I get is from the noise, and as we discussed, the noise has the same distribution regardless of theta. That was our assumption. This, because of Cij, is independent of theta. So sigma 1 is equal to sigma 2, and let me just call that sigma, and I just need to calculate it. Right? So we wrote already what is mu1, what is mu2. Obviously, as we discussed, the optimal decision point will be just the mean of them. And what will matter for the error is the ratio between sigma and the difference between these two values. That's all that matters. What determines this area is, again, the ratio between sigma and the distance between these 2 points. Okay, so let's calculate sigma.
Can you explain again why the ratio is there?
Well, first of all, clearly, if I would move around these plots, if I would change mu1 and mu2, if I would add something constant to mu1 and mu2, this would not change, and keep sigma fixed, this would not change the area under this. Right? If I would shift all this plot to the right or to the left, it does not change this area. What do I need to calculate? I need to calculate to calculate this area, I need to calculate the area behind below a Gaussian that starts at this point. What is this point? It's mu1 plus mu2 over 2. And so let's just shift this whole graph such that mu1 will be at 0. Then now it's a Gaussian centered around 0, and I need to calculate the tail of that Gaussian beyond the point, which is mu1 plus mu2 over 2. Sorry, which is yeah, it's now mu. Yeah. Okay, we'll do it late. You know what? We'll just do it mathematically in detail a bit later. Okay? So you will see.
So just what determines the error?
But my argument, the way to think about it, I will answer your questions in a moment. The way to think about it, another way to think about it is just to think about units. I mean, how should I say it? If suppose that the Ri had some units, then L would have, and W is dimensionless, and L would have these units. We have to generate something which does not have dimensions. I mean, it's clearly the difference between mu2 and mu1 that matters, and not their absolute values, because of what I said, that if I shift this plot, if I add something both to mu1 and mu2, it will not change this area, right? So it's clearly the difference between them. And I claim that it's also not just the difference, it's the ratio between the width of these Gaussians and this difference that matters.
I think it's equal or proportional to the ratio?
No, it's not equal to the ratio, it just depends on that ratio. It can have, as you will see, it has a complicated dependence on that ratio, but it depends only on that ratio. If I would, another way to say it is if I multiply sigma by a factor and multiply this difference by a factor, then the area under this will not change. And you will see it in detail. If you don't believe it, you will see it in a bit later. So for now, what I want to do is to calculate sigma. And so let me write sigma squared, the variance of this distribution. So I can write it as follows. I take the response, I subtract the mean response. I take the L. Okay, this is L. I subtract the mean of L, which is sum over I, Wi, Fi of theta. I square this. And this, by definition, is the variance, right? Which theta? Okay, what am I averaging over? I'm averaging over the distributions of the responses given theta. Which theta? Doesn't matter. This will be the same regardless of theta, and we're interested specifically in theta 1 and theta 2, and this will give us sigma 1 and sigma 2, which are the same. Okay, so let me write this a little bit differently. I will write this as sum over I, Wi, Ri minus Fi, and I will write the squared sum as the sum over I multiplied by sum over j. So I'm doing it a bit with skipping some steps. I will write this as sum over I and j, Wi, Wj, Ri minus Fi, Rj minus Fj. And now I need to take the average. So this is just what is inside this average. I need to take the average. The average is over the distribution of R. Wi from our point of view are now fixed. So nothing to average. I can put on. I can put the average. I can take this out of the average, the Wi, Wj. So I can write the average only on these terms. Okay. Now, what is that? Yeah, that's the covariance matrix of the noise. And by definition, by the way we constructed it, this is Cij. So what we have here is sum over I and j, Wi, Wj, Cij. And now let's write the probability of error. So I will write down the probability of error under the assumption that theta is theta 1. But you can convince yourself easily in a moment later that it's also the probability of error if theta is equal to theta 2. So I should have written pre-error is half times the first one and plus half times the second one, but they're equal to each other, so I can just write one of them. So I need to calculate this area. What is that? So we have a Gaussian, and we need to take the Gaussian, integral of the Gaussian from this point to infinity. So this point is mu1 plus mu2 over 2. And now I need to write down the normal distribution, which is 1 over square root 2 pi sigma square, exponent of minus x minus mu 1 squared, because we're dealing now with the response given theta 1, so its mean is mu 1, divided by 2 sigma square dx. And you know what, I was planning initially to just skip some points, but maybe just to clarify why I said earlier that this depends only on the ratio between sigma and mu1 plus mu2 minus mu1. We can define a variable, let's call it u, which will be x minus mu1 divided by sigma. Okay, so du is dx over sigma, right? And when x is mu1 plus mu2 over 2, then u is mu2 minus mu1 over 2, right? Do you agree? When I plug in x mu1 plus mu2 over 2, divided by 2 sigma. Okay? And so this is an integral going from mu2 minus mu1 over 2 sigma. This is this lower bound. And when x is infinity, u is also infinity, so the upper bound remains infinity. Now, dx, as I wrote now, is sigma du. Or, so dx over sigma, which we have here, we have dx over sigma, is just du. So I can write here du divided by square root of 2 pi. And now here we'll have x of minus u square over 2. Right? So everything here now does not involve any parameters. The only parameter that remains is this. What?
What is the exponent?
Here, u squared. So I just rewrote it as in terms of this variable, and no parameters here remain. So the only parameters in this integral is this one, and you can see explicitly that it depends on the ratio of mu2 minus mu1 and sigma. Okay? And furthermore, this is nothing but a complementary error function up to the the definitions, the prefactors of how it's defined, which I never remember, so I always look it up. And this is half the complementary error function of, I will write it as follows: d prime over 2 square root of 2, where d prime, just to conform with the conventional definition of discriminability, which we discussed already. So d prime square, by definition, is mu2 minus mu1 squared divided by 2 sigma squared. Sorry, without the 2. Okay, so it's just a way to write it as a function of this quantity. Okay, but now I can plug in in this expression, what I know is mu2, what is mu1, and what is sigma. So first of all, in order to have a small likelihood of error, for the probability of error to be small, we want d prime to be large, right? We want the ratio between these means to be large compared to the width of these Gaussians. And now we just need to ask ourselves, I should plug in here what is mu2, mu1, and sigma as a function of w, and ask myself what is the best choice of w such that this prime will be as large as possible. So let's do it here. So d prime squared let me add another definition here. So you see that everything will depend. So mu2 minus mu1 is sum wi si plus minus fi minus. So it all depends only on the difference between. It doesn't matter what is the absolute response of the neurons to theta 1 and theta 2. It matters what is the difference between the responses to theta 1 and theta 2. So it's convenient just to define gi as fi plus minus fi minus. And in terms of gi, what we have is then sum over I wi gi squared divided by sum over I and j wi wj cij. And in vector notation, vector and matrix notation, I can write it as G transpose W squared divided by W transpose C W. Okay, so this now is a function, the probability of error is now a function of the choice of the weights, and I want to find the weights that will minimize the probability of error. So I need to take a derivative. To find the optimal weights, I need to find weights such that the derivative of this quantity with respect to W is 0. So so optimal weights, I need to solve the set of equations d prime squared to dwi equals to 0 for all I. So so in general, what? Paul? Okay. So in general, one thing which is a useful thing to remember whenever you have to deal with an optimization of something which is a ratio of two things is that if you want to require that if you have something which is a ratio of two things, as we have here, and we're looking for the derivative of this with respect to some parameter x, and we want that to be 0, I will leave it for you to check if you're not convinced. Maybe for some of you it's clear that this is equivalent to the equation that n prime divided by n is equal to d prime divided by d, where by prime I mean derivative with respect to x. Okay, so I will just use that immediately to write these equations. So I need to take the derivative. So I want to take the derivative to do this with this expression and with wi. X is now wi. So for the numerator, I have 2g transpose w multiplied by the derivative of this with respect to wi. What is that? gi, right? What I wrote so far is the derivative of the numerator with respect to wi, and using this recipe I need to divide by the numerator, and I want to require that this is equal to the derivative of the denominator divided by the denominator. So what is the derivative of the denominator with respect to wi? So we can see this by looking in this expression. If I want to take the derivative with respect to wi, I will have sum over j wj cij, but there's actually a factor of 2 because wi appears both here and here, so there will be 2. So this is equal to 2 sum over j wij cij, which is nothing but C, the matrix C, multiplied by w, the ith element. You know what? Let me write it explicitly. Sum over j cij wj, and this is, and now I need to divide by w transpose c w squared. So these are the equations that we need to solve. They look complicated, but in fact they're remarkably simple, as you will see in a moment.
Why squared?
Because no, there's no squared. You're right. Thank you. Okay, so this looks complicated, but in fact it's very simple. These equations. The key to realizing that they're very simple is to just ask what here depends on I. So there is some number here. This is a scalar which does not depend on the index I. This is another scalar that does not depend on the index I. This is another scalar that does not depend on the index I. So you see that if I think about these equations as telling me something as a function of the index I, these equations are telling me that gi is proportional to sum over j cij wj. And when I say proportional, I mean that the proportionality constant does not depend on I. Now furthermore, I claim that that's all I need to know, because from the start I can tell I don't care about the prefactor of w. If I take a set of weights, okay, I erased the definition of L, but I claim that if I take a set of weights and multiply all the weights by the same constant, the discriminability will not change, because it will just multiply mu by that constant and multiply sigma by that constant. You can see also from these equations that if you have a set of w's that solve these equations, and you multiply w by all the elements of w by the same constant, then it will just fall from it. You'll still have a solution of these equations, right? You will have that constant here divided by that constant squared, and you'll have that constant here divided by that constant squared. So, but we could have guessed it from the start. If we change, all that matters is the direction of w in the space. The magnitude of w doesn't matter at all, because I can always adjust I multiply w by a constant, set the threshold to be multiplied by the same threshold, by the same constant, and I'm implementing exactly the same discriminator. So from the start we should have known that the magnitude of w, the direction of w matters. The magnitude of w doesn't matter. So if I know this, I actually know what is w. I don't care about the prefactor here. Fine. So now I know what is w, right? Because this means that the vector g is equal to the matrix C multiplied by the vector w up to some constant. Okay, that I can pick as I wish, and therefore w, the optimal w, is, I can choose it to be anything proportional to the inverse of the matrix C multiplied by the vector G. before we take the break, let's just write down what is discriminability. What is d prime square for the optimal choice? So we need to plug this in here. So the optimal discriminability, that for the best possible choice of the weights, okay, so we have G transpose C minus 1 G squared divided by W transpose. So if I take a transpose of a vector, of a multiplication of some matrices vectors, I reverse the order and do a transpose on all of them. So I have here G transpose C minus 1 transpose, and then I have here C, and then I have again W, which is C minus 1 G. C is a symmetric matrix. It's a covariance matrix. So the transpose of itself and also is it the same as itself, and also the transpose of its inverse. So this, I could remove this transpose. And you see that C times C minus 1 cancels. This is unity. So actually in the denominator I have the same thing as what I have here, just not squared. So I end up with G transpose C minus 1G. And therefore, let me just write it down here and frame it. So this is G transpose C minus 1G. Okay. So I think now we can take a break. Yeah. it's basically this or something. Yeah, it's exactly
So it's a
it's
vector.
exactly this. No, it's no, G is a vector.
Because it's multi-dimensional.
It's multi-dimensional. Ah, right. Mu is the. You're right. I was wrong. Mu is the expectation value of the L or something.
Yeah.
So no. So G is the F1 minus F2 minus F1, F plus minus F1.
No, no.
Not exactly. It's I don't think it's written here anymore. But
Yeah.
we had F plus and F minus. The expectation value, the vector of expectation value, right? The mean of the multi-dimensional. So G is the difference.
So it's the difference is not the true difference. Like
You have one multi-dimensional Gaussian if you condition on theta 1 and another if you condition on theta 2.
Yeah.
Both of them have means, like a vector, mean vector, right? One, the first one is F minus, the other one is, yeah.
So here it is.
Yeah, to get this no, you don't see it from here. You see this from, whatever, from them. When you substitute W to be WR. We derive this,
Yes.
but we can express the sigma and the mu as a function of G and C and W, right? So that's what we did out. And then we derive this to maximize with respect to W. And when we find W opt, we went better and substituted and we got this. Like we did the argmax and then we asked what is the max.
Then choose calculation.
Why is this? Where did this come from? Like this thing?
Yeah.
Yeah, it's like from the rule of how to derive a ratio thing. Because it has this minus. You derive the denominator times the denominator minus the derivative of the denominator times.
Yeah.
It's extremely ugly algebra that you always make mistakes. At least I always make mistakes in.
So it's like yeah. Usually if you divide it with data.
Yeah. All right. So now this, and you want this to be equal to 0. It's not like so this cannot be 0. Oh, at least we assume. But probably it's true only if this is not 0 and then you
כן. שיהיה ביום שישי. עכשיו חשוב במצלם. כן, זה גם בסדר כללי, אבל הוא אמר שזה במטרות ולהתחיל. אפילו בשעת...
הראשון. שבוע לפניו.
כן, אני עברת לא רוצים
מוכר לשבוע.
זאת אומרת, בעוד חודש, וקצת אנחנו מדברים, שבת תיכנס בדיוק, או כאילו, נתחיל לבשל, ביום. ב3 שעות, כאילו, רק לחזור הביתה, הגענו לחצי שעה, ואז נגיע בשתיים, אני גם לא יכול לנסוע למכון חצי שעה. אבל אם מתחילים ממש מוקדם, לא, או שיש מבחן של 3 שעות, כאילו, 8 3 שעות.
שזה אגב תמיד יהיה לטובה.
העניין שיש להם
אנחנו מראש למבחן לפי כמות הזמן שאנחנו לתת לו.
מה?
יש להם פשוט נטייה להאריך את המבחן, זה לא שאני אומר.
מבחן שהוא עושה בזמן של הקורס.
הם לא מתכננים אותו.
זה היה 4 שעות, ואז כאילו... כאילו אם לא נעשה בסדר את המבחן שאני מרגיש שאני זמן.
לא נעים, כאילו לא נזיק
זה... אם...
אולי נקנות אוכל לשבת. נתרום לך.
לא,
אני בודקת כי יש לנו אוכל, אני לא מנסה לעשות.
בואי נראה. אם כולם בסדר עם זה, כאילו לא יודע מה, כאילו... יוכל לפחות יארוחה אחת, אז לפחות חנות בשבת.
לא כולם בסדר עם זה.
כן.
אתה לא צריך לשאול אם זה בסדר, לא צריך קודם לשאול אם זה בסדר מבחינתנו, אנחנו קודם שואלים אם זה בסדר מבחינתך. ואתה יכול לומר לו, כאילו פרקטיקה לזה.
זה נראה לי לא... פרקטיקה זה נראה לי לא... כאילו, אם זה לכולם זה יעבוד, אז כאילו...
אבל גיל, זה לא שואלים.
אני לא אגיד לא, אם זה התאריך היחיד שמצאנו אחרי חודש אנחנו חושבים על זה, וזה גם נותן כמעט פעם. כמו ששמתי לכמה זה מודבש למילואים שלה. אם זה עובד לכולם, אז כאילו. אני כן.
ואין שום תאריך מבחינתך עד ה-18 שלי?
השבוע של ה-12 יש לי מבחן בשני ורביעי, זה בדיוק שני המבחנים הגדולים שלי.
מתי נגמר? אני שואלת.
כן, יש לי מבחן אחד ביום שני, אבל יש 3 שבועות, מבחן אחד ביום רביעי, יומיים אחרי, אז מבחינתי השבוע זה ממש מעדיף, כאילו כל יום אחר זה יום ראשון.
18 זה יום ראשון?
כן, נראה לי, כאילו, המילואים שמתחיל 18, איך מתחיל מילואים?
I'm doing it now, I don't know why.
כאילו, השבוע שאחרי כבר אפשרי מבחינתי.
כן, אבל גיל במילואים. שהוא קבע מבחנים.
זה גם לא שואלים אותי, אגב, יכול להיות כאילו שברגע האחרון יתבהר לי שאני כאילו בחצי של המילואים אבל הם מחכים את זה שתסתדר. זה דברים שיודעים ברגע האחרון.
כן,
כאילו אתם אף אחד לא רוצה כמו שבא לך כזה טוב.
לא, זה החלטתי שהמבחן הוא ברביעי.
לא, ואז אני לא יכול להגיד חופש עד לא יודע 25. אני לא יכול לומר את זה.
קשה.
לא, אם כולם בסדר אותי...
אנחנו חייבים לסדר את המצלמה, פשוט תצלם בלבומים כנורמלי.
אני יכולה לשחק את הטבעי שאני כותבת.
ממש, אבל באופן כללי זה יהיה שידור בחיים שלנו.
כן.
למה רביעי זה לא טוב עוד פעם?
יורם בטיסה בזמן המבחן.
אפשר לעשות מבחן אחת צהריים.
קנו את רשתות א' שכאילו... קנו את רשתות א' שיונתן לא היה פה.
כן, נכון, אני גם חושבת.
אני גם לא חושב שכן.
אבל אני חושבת שזה,
היה נשמע כאילו נפלאה, ואם אתה רגע מנסוע, אתה לא מוכר, אבל אם כולם מסכימים איתם, בוא נגיד ככה, עוד שבוע למידה ושעה פחות במבחן שמקסימום אני אצא, זה ייצא. אז כאילו... עוד פעם, אם זה 9, אבל אז לא, אם...
נוגה, אני יכולה לשאול את עדי, מעבודה של מתי, על התשיעי?
יש לנו הרבה ספרים בבית.
וואי, זה קשה.
כן, אני מבין.
כי גיל אמר, זה לא הכי נוח. אנחנו מדברים עכשיו על התשיעי.
אבל...
זה יום שישי השחר, שבוע
כן,
אחר.
שבוע אחר כך. סליחה, זה קודם כל.
קודם כל, במילא אני לא רואה, אבל... לא, אני לא יודע.
כאילו חשבנו על צהריים, לא ידענו קצת.
אז זהו, צהריים זה קצת פחות טוב, כי זה ממש אמצע לילה בשבילי. אני אהיה בברקלי, זה 10 שעות הבדל. אם זה בבוקר זה עוד כאילו לילה לא נורא מאוחר, אז...
כמה זמן יהיה המבחן? כי בשבילי יום שישי זה ממש
יש פה נטייה של מבחנים ארוכים. אם נלך לפי מה שקרה בשנים האחרונות, אז זה כאילו פורמל נטייה 3 שעות, אבל בסוף נתנו הערכה.
של כמה? 4 או 5? 5.
לדעתי יותר קרוב לאולי 4.5.
וואו, מבחן כזה.
אבל אפשר גם... אני חושב שאם זה ביום שישי ויש לאנשים ביד, אנחנו... נדמה לי, האמת שצריך לשנות נטע, אני לא זוכר.
אפשר להתחיל גם מוקדם יותר.
אני חושב שבשנה האחרונה עשינו מבחן יותר קצר.
אנחנו בעד. כי הארוך הוא...
זה מתיש.
באופן כללי, אם נדע מראש מתחילת המבחן מה האורך שלו, גם אם הוא ארוך או קצר, זה תמיד לטובה.
באורך רגיל של 3 שעות.
לא, מה שקורה לפעמים זה שעושים...
אבל עושים מבחן שהוא לא סביר לאורך. כל המבחנים
לפעמים
שלנו
קורה
עד עכשיו
בסוף
לא
שבכל
סביר
זאת.
לאורך. לזמן.
טוב.
כאילו אף אחד לא סיים אותו בזמן. אני מניחה שזה... טוב, תאריך...
בכל מקרה, אני מעדיף, אם אתם רוצים שאני אהיה, אז עדיף שזה יהיה בבוקר ולא לא יתחיל בצהריים.
בוא נתחיל ממש מוקדם, באזור 9.
אתה מדבר על יום שישי? או דיברת על רביעי?
תראו, נניח שמתחילים ל-10, זה לא נורא, זה חצות בשבילי. לא, ברביעי אני פשוט לא, אני במטוס.
לא, אני מדבר על שישי כמה יותר מוקדם, עדיף לי, כי אז אני יכול...
אבל בסדר, מה זה כמה שיותר מוקדם?
זה ליטרלי כמה שיותר מוקדם.
אני חושב שיש אנשים שקשה להם עם שעות מוקדמות.
השאלה היא מה איפה... כמה מוקדם שם?
נכון, אולי 9.
אין אף תאריך. We're talking now about the 9th, which is the Friday after week after
Okay, let's do this offline, not now. Okay, I want to summarize what we've found so far. So I will write it here. The probability of error is half the error function of d prime squared divided by, d prime divided by 2 square root of 2. So this is some function, monotonically decreasing function of d prime when d prime is 0. What is the probability of error? Half. I mean that d prime, you can see also from our expressions that say if the two responses are identical in the two neurons, mu2 is always in the two non-neurons, but the two conditions, then mu2 will be equal to mu1, d prime will be 0, and in that case probability of error is 0, and then it's a non-monotonic, highly nonlinear function. When d prime is large compared to 1, the probability of error is extremely small. Okay, and then we got expressions for d prime in terms of for the optimal weights and for the d prime in that case. So the optimal weights were c minus 1 g, and there is a prefactor that you can choose as you wish. So maybe I will write like this. and the d prime square optimal, d prime without square, optimal is G transpose C minus 1 G. So,
so the d prime square, why is it equal to d prime?
what's the question again? Why is that
Because
true?
d prime is equal to GC C minus 1G.
Because I derived it. I took this expression and I...
No, but you said also the d prime, not square, is equal to it.
No, it's without a square.
Yeah,
But here it's with a square. So there is a square. Sorry. Thank you. You're right. There is a square. Let me just go through my notes and make sure that I did not put it in. Okay. I think it's with a square. I just wrote to you what is d prime square, so this needs to be checked, but I think that this is a correct. I think it is with a square. Okay, so so this is general. This is for any choice of the G's and any choice of the covariance matrix, and I will do in a moment some examples. But I just want before that to look at these expressions and see that they make sense. So that's a few things to check, which are kind of trivial, and it's always good to check things like that. So if G is 0, G0 means that the response to the two neurons, to the two conditions, theta 1 and theta 2, are the same, right? Or in other words, if Fi plus minus Fi minus is 0, then the vector G is just a vector of zeros. And then d prime is 0, and we cannot discriminate. We have a probability of error of half. So the larger, in the basic sense, the larger the difference between the responses to the two conditions, the better the discriminability. And C is a covariance matrix of the noise. So just qualitatively speaking, if there's lots of the noise has large variance, then C, the matrix C, not the inverse of the matrix, the matrix C has large elements, the inverse is small. So lots of noise makes this thing smaller, which also makes sense. Lots of noise decreases tends to decrease the discriminability. Or in other words, if we would multiply the covariance matrix by a factor, not changing its structure, but multiplying it by a factor, then the discriminability will always decrease. Okay, so now I want to do some examples. Consider some examples, and the examples that I will do are motivated by the simple examples that I discussed with you in the beginning of our discussion on correlation. So I discussed an imaginary situation with two neurons, and now I will do it with n, but still, I hope you will be able to see the similarities. So the first example that I want to discuss is n identical neurons, and which are also uncorrelated. And I want to see that what we get from this expression makes sense. So GI, which is Fi plus minus Fi minus, we assume that it's the same for all the neurons. The neurons are identical to each other, independent of I. And the fact, if the neurons are uncorrelated, it means that the covariance matrix is diagonal. So let's denote it by A times the unity matrix, and I'm assuming that it's the same value on the diagonal because I'm assuming that all the neurons are equivalent to each other. Okay, so what does this formula tell us? What will the optimal weights look like? It looks like G multiplied by A. Okay.
by the power of
So remember that we discussed before that actually the magnitude of the weights doesn't matter anyway. So what can we say about the optimal weights?
proportional to G.
Okay, which
Uniform.
uniform. The crucial thing is that the optimal weights are independent of the index I. They're the same for all the neurons. If we take this matrix, its inverse is also proportional to the unity matrix. We multiply it by G, which is a vector which has the same entry everywhere. We get again a vector which has the same entry everywhere. What is the entry? Doesn't matter because from the start the magnitude of W doesn't matter. So we can just say that the optimal weights are some number, W. You can choose it as we wish, it doesn't matter. What can we say about the optimal D prime? Okay, so now we need to take this vector, which is a vector of G's in every entry, and make a sandwich with this vector around this matrix. So we'll have the prefactor within this vector, which is G. The value within this vector will appear twice, both here and here. And from the matrix C minus 1, we'll get 1 over A. The inverse of this matrix is just 1 over A in every element. And then all this is multiplied by the vector of 1, 1, 1, 1, 1 times a matrix that has 1s in the diagonal times again this vector. So what does that give us? What does that give us? This matrix times this vector. This is unity matrix, so it's just this vector. And then when we take this vector multiplied by itself, what do we get? Number of neurons, n. So we get n G squared over A. So this is the optimal discriminability. So you see that the larger the number of neurons, the better, right? Larger the number of neurons, the better. The larger the difference between the response of each neuron in the two conditions, the better. The larger the variance of the noise, the worst. More noise, detrimental. But you also see what happens here. We take our neurons. Our discriminator is just summing up their activity. So it's clear why we get a discriminability that scales like n. The sum of the activity of all these neurons is also normally distributed. It has a mean which is n times the mean of a single neuron. And it has a variance which is n times the variance of a single neuron. So the standard deviation is square root of n times the standard deviation of a single neuron. So when you have more neurons, the ratio between the standard deviation and the mean of the whole and the sum of all the whole response it becomes smaller. So it's less noise. We average over the noise. Let's check another trivial case, which is n identical correlate. Well, actually, I will not do it trivial. I will do it a bit. Right? So I will want to do n identical and correlated neurons, but I won't do fully correlated. So let me explain what I mean by that. So identical, first of all, means that GI is still going to be independent of I. And the correlation matrix that I'm going to assume because I'm assuming that all the neurons are equivalent to each other, it will only depend on whether the index I is equal to J, which is the covariance, the variance of a single neuron, versus the covariance between two different neurons. So I want to write a matrix here that has a certain value in the diagonal and some other value elsewhere. So one way to a way to write it. So maybe first I will write explicitly what I mean. So as in this case, I will put an A here and put 1s over here on the diagonal. So if now I would put zeros everywhere, elsewhere, this will be the case that we already discussed. But now I will imagine that there is some other value in all the elements of the covariance matrix which are not the diagonal. So, yes, the same. And the same because if I'm assuming that all the neurons are equivalent to each other, it means that it cannot depend on the index of the neurons. So, the variance of a single neuron is A, and the covariance between two neurons is alpha times A. Let me write this matrix in mathematical notation. So it's if I is equal to J, we have A, and if I is different from J, I want to get alpha A. So I will add here alpha times 1 minus delta Ij. So this is this matrix. Now, before we continue to calculate the optimal weights and the optimal discriminability, I want to discuss a bit what this matrix, what values alpha can take. So first of all, if alpha is equal to 0, we're back in the uncorrelated case. Now, what is alpha? What happens if alpha approaches 1? Or let me write, if alpha is equal to 1, what happens then?
1 higher than fully correlated?
Yeah, if that's right, then the correlation between any two neurons is the same as the covariance. So this is a fully correlated case. And in fact, the only way this could happen is if the responses are identical. Okay, this means that the neurons that the responses of all the neurons are identical on a trial by trial basis. Turns out that alpha cannot be larger than 1. What was the question?
I mean, is it an assumption or is it something?
No, it turns out. So how could we hope to? Why can I say something like this? This alpha. How can I show that there are some restrictions on alpha?
Neuron A equals alpha neuron B, and neuron B equals alpha
Yeah.
neuron A.
Yeah, so it doesn't make, okay, but, well, it's not equal. It's, this is the structure of the covariance matrix. Right?
It's still
Okay, so,
not together.
so the way to ask really what values of alpha are possible is to remember that this matrix has a property that it always has to obey, and this is a positive definite matrix. Okay, covariance matrix is always a positive definite matrix. No matter what distribution you choose for the elements, it always has this property. And meaning that, for example, all the eigenvalues of this matrix must be non-negative. And so you can show that if alpha is larger than 1, this matrix has negative eigenvalues, and there's no distribution, no way to realize such a matrix as a covariance matrix.
Is this true for covariance matrix in general?
Yes, any covariance matrix is positive definite.
No, I mean,
Yes, any covariance matrix is positive definite.
talked about the restriction on alpha, but is it just a special case because everything?
Well, the reason that any covariance matrix is positive definite is that if you have some vector u which has some distribution, okay, any distribution, and you want to calculate the mean of u, some linear, and you want to take some, and so suppose that u has a any distribution, not just Gaussian, not just normal, any distribution with a covariance matrix C, and you want to take some vector, some linear combinations of the elements of U. Something like, so let's choose some vector V transpose and multiply it by U. And now you want to ask what is the variance of this variable. You can prove that the variance of this variable is the sandwiching is V transpose C minus 1 C V. And the variance is always positive. So that means that if a matrix that has the property that for any choice of V, this quantity is always positive, is positive definite. So this is a way, I'm not doing it in detail, this is the way to prove that any covariance matrix has to be positive definite, or non-negative definite, but semi-positive definite.
But I asked about the restrictions on alpha.
Yes?
And you said that alpha cannot be larger than 1, right?
Yeah.
So is it just for this form for covariance matrix that all elements besides the diagonal are the same, or it's a general fact about
well, if I didn't, the definition of alpha is through this definition of the matrix. So, I mean, any covariance matrix has to be positive definite. If I choose if I want to generate a covariance matrix that has the structure, then if I cannot choose alpha to be larger than 1, because then it will be not positive definite. And I want to also highlight what's the problem with this. We wrote explicitly the Gaussian distribution, right? It was 1 over Z exponent of R minus mu minus F1, or if I call it F minus, or F, C minus 1, R minus F. So what's the problem with this? If I could choose, it seems like I can choose the matrix C to be whatever I want. But if I choose the matrix C to be such that it's not positive definite, this is not normalizable. That's a problem. It's like having in the case, let's just imagine the one-dimensional case. In the one-dimensional case, not this example, it will be like this matrix would be positive definite if C is a number, it's a variance, and it has to be positive. If that number is negative, I'm trying to normalize, there's a minus half here. If I have something that looks like x of r squared divided by some positive number, because there is a minus and this is negative. So I have something which is not normalizable. It's a distribution which is not normalizable. So we can define a Gaussian multidimensional variable only if the covariance matrix that we try to put in it is positive definite. Otherwise, there are directions in which the Gaussian diverges instead of going to 0. Okay, so going back to this. Now we have a parameter that we can tune, and as we tune this parameter, we go from, in one case, when alpha is equal 0, to the completely uncorrelated case, up to the fully correlated case. And we have the machinery to calculate what are the optimal weights and what is the discriminability. So let's plug this in. Okay, in order to do that, we need to invert this matrix, right? So the question is, how does the inverse of this matrix look like? Yeah, but just this matrix has symmetries in it, that it has a certain value on the diagonal and some other value anywhere else, which means that any two neurons are equivalent to each other. So what can we use that? How can we use that to find the inverse?
It will be of the same form.
Yeah, exactly. So the inverse matrix. So if this is C, I claim that without doing any work, I know that I could write the inverse of C in the form B, 1, beta, beta, okay, something like this. Because every two neurons are equivalent to each other, so there's no reason that the element of the inverse between some particular pair will be different from the element of the inverse for some other pair. So this I know without doing any work. Now we need to multiply these two matrices together and require that we get the unity matrix. And in this way, we can find what is this B and what is beta. Okay, so I will not do that explicitly. I will just write the answer. B is equal to 1 over A times n alpha plus 1 minus 2 alpha divided by n alpha plus 1 minus alpha. There's a risk here that alpha and 2 in my handwriting can be similar. So if you're not sure, ask me. 1 minus alpha. What can I do? That's what it is. It's ugly, but that's what it is. And B and beta is equal to minus alpha divided by n alpha plus 1 minus 2 alpha. Okay. What can we say about the optimal weights? So G is a vector which has the same entry everywhere.
They're also the same.
Yeah, they're also the same because there's nothing. If we multiply this line by a vector that has the same elements everywhere, and this line, we'll get the same thing, right? So the weights are still independent of I. And it makes sense. The neurons, there's nothing that differentiates the neurons from each other, so there's no reason we would choose different weights for different neurons. Okay. So this result, it's nice to see that it works out this way, but we could have guessed it without doing any calculations. And the key now is to calculate the optimal discriminability. So we will have G squared times a vector of 1 multiplied by C minus 1 times a vector of 1. Okay, so what is that? What actually do you get when you sandwich a matrix between these two vectors, this vector on both sides? You get the sum of all the elements of the matrix. So we have two types of elements in this matrix. We have the diagonal elements and we have the non-diagonal elements. So we will get G squared times n times B, these are the diagonal elements, plus n times n minus 1 divided by 2, which is the number of non-diagonal elements, multiplied by B times beta. Right? Okay, why did I divide by 2? There's no division by 2. It's n times n minus 1. That's the number of non-diagonal elements. It's n squared minus n. We need to count both sides of the diagonal. Okay, so I can write this also as G squared. Everywhere here there's an n, so I can take one n out, and there's a b everywhere. So G squared nb times 1 plus n minus 1 times beta. And now we need to plug in the expressions that we have for b and for beta. Unfortunately, this looks like a big mess, but when you do everything, collect terms, you get something which is less of a mess than what you would expect. So the expression that we get is G squared over A times n divided by n minus 1 alpha plus 1. And now I want to look at this expression and see whether it makes sense. So, when alpha is equal to 0, that's the uncorrelated case. What do we get? G squared times n divided by a. That's our previous example, right? When alpha is equal to 1, that's the fully correlated case. Then I have here n minus 1 plus 1. So n and n cancel, and I just get g squared over a. Does this make sense?
We had one.
Yeah, if I have n neurons that each time I observe them, they give me the same answer, it's just like having one, right? And if alpha, what is more interesting a bit is to look at alpha which is between 0 and 1. And then we have a function. Then we have a function of n, right? And initially, when when n is very small, because we have here a 1, so initially we can forget about, initially we usually suppose that alpha is small. So initially, when n is small, this term is negligible compared to this one, and you see that the behavior is like the uncorrelated case when I start to add more neurons. But at some point, this term becomes comparable to 1, and eventually it wins over. And when it wins over, we have here something which is proportional to n, so we will saturate. So this function, if I would plot it, d prime, will start growing as in the uncorrelated case, and then at some point it will saturate. And we can write down what is the behavior for large n. So d prime square, when n goes to infinity, we can forget about this, so we have just 1 over alpha. So we have g squared divided by a alpha. So remember, alpha is smaller than 1. So we get a better discriminability than for a single neuron. But we saturate. At some point, when we add more and more neurons, the fact that they have some partial correlations between them mean that at some point we don't gain any more by adding more neurons. Okay? All right. Let's do another example, which will be illuminating. So we have now, let's imagine that we have 2 populations of neurons. With opposing responses. So I imagine that one group of neurons increases its responds more to theta 2 than to theta 1, and the other one responds more to theta 1 than to theta 2. So my model will be that GI, which remember is Fi plus minus Fi minus, is some positive number or some number for the first for half of the neurons. So I assume the number of neurons is even, and it's opposite for all the other ones. Okay? And for Cij, I will still assume the structure that we discussed in the previous example. So the neurons are all, the noise is partially correlated, and it does not care about the identity of the neurons. So it's A delta Ij plus alpha 1 minus delta Ij. So C minus 1 is still this. Nothing changed in C compared to the previous example. So with these particular values of B and beta, I will erase it just to continue, but we will use these values. Okay, so still C minus 1 is B times 1 beta okay. Okay, what can we say about the optimal weights? What is the structure now of the optimal weight? So remember, to calculate the optimal weight, we need to take this vector, this matrix, and multiply by this vector. What would we get?
The G of that neuron, the GI.
Not exactly, no. Remember that actually the value of the weights doesn't matter. It's just the structure, the direction. What kind of vector? So in the previous examples, we got a vector that has the same entry in all positions, right? What changes now? So I have some matrix with this structure, and I multiply it by a vector that has G times 1, 1, 1 up to this point, and then minus 1, minus 1, minus 1, minus 1 up to this point. No, it would be 0 if beta was 1. But beta is not 1.
The vector of the 1 and the minus 1.
Yeah. So that's what happens.
It's the same as G, but normalized.
This is what you meant. This is what you meant when you said G, that it's a vector G. Then you were correct. So, actually, you see that the only thing that matters is whether the 1. So we multiply a line of this matrix by this vector. The only thing that matters is whether the 1 falls in this part or in this part. And you can convince yourself that the answer will change signs in these two cases. So the optimal weights have the structure W, some W. Remember, we can choose it as we wish. Times 1, 1, 1, minus 1, minus 1, minus 1, minus 1. Does this make sense? What does this discriminator do? The discriminator takes these weights and multiplies them by the neural responses, right? What does it do? Yeah, it sums the population that increases its response, and just subtracts the response of all the neurons from the population that decreases its response. It makes a lot of sense if that's what it's doing. What about the discriminability? So for the discriminability, we need to take this vector, sandwich it around C minus 1. So we have G squared times 1, 1, 1, 1, minus 1, minus 1, minus 1. C minus 1, 1, 1, 1, 1, minus 1. Okay, so something like this. And So this is the matrix C minus 1. So in order to do this, it's convenient to think about this matrix C minus 1 is composed of 4 smaller matrices. One is a matrix that has 1s on the diagonals here and beta here. This one also has exactly the same structure. So these two smaller matrices exactly have the same structure that C minus 1 had for the full n. And then here we have matrices that just have betas over everywhere. Right? And so when we take this sandwich of this vector around C minus 1, we will get a contribution from these terms, which is a sandwich of these terms around this matrix. We'll get another one from this and this around this matrix, but it will be the same, because there's a minus sign here and a minus sign here. And then we'll get a sandwich of this vector with plus 1s and minus 1s around this matrix. And we'll get it again from this and this around this matrix. So let's do it explicitly. So I will write down a 2 because everything will have twice. We'll have this sandwich around this matrix, and it appears twice again from this part. So let's write that part down. So this part actually has the same structure as what we did in the previous example, except that n is replaced by n over 2. So we get 2g squared b times n over 2 plus n over 2 times n over 2 minus 1 beta. It's exactly what we wrote again in the previous example, except that I replaced n by n over 2. And it appears twice. And then we have these terms where we have 1 multiplied by this matrix times a vector of minus 1. What will that give us? So I claim that it's because there's here a plus and here a minus, there will be a minus sign, and then just the sum of all the elements in this matrix. So we have plus 2 because we have it twice, times minus 1, times n over 2 squared, that's the size of the matrix, times beta, times b times beta. There was a b here in front of all of this, right? Times b times beta. Okay, this looks even worse. Now we need to plug in the expressions for b and for beta. And so this looks even worse than what we had in the previous example. But actually, when you do all the math, you get an even